So let's continue with module 7, Ethernet switching. Okay. Again, the concepts we study here, you will see they overlap with some of the items that we have studied in the lecture. So we will go through Ethernet frame, which explains how the Ethernet sublayers are related to the frame fields. We will go through the Ethernet MAC address, MAC address which resides on your NIC network interface card. We will look at the concept of the MAC address table. It explains how a switch builds its MAC address table and forwards frame. Inside a switch, it has got its own MAC address table, which has the address of every MAC, every device on the network. We'll also look at switch speeds and forwarding methods. Describe switch forwarding methods and port settings available on layer 2 switch ports. So these are some of the things we're going to look at in this unit. This topic. So looking at Ethernet frames. Ethernet operates in the data link layer, layer 2, and of course the physical layer as well. It's a family of networking technologies defined in IEEE 802.2 and 802.3 standards. Okay, I told you before, if you go on IEEE websites, you can get the RFC, request for comments, for all of these standards. You can download them and study them in detail. So in future, when you're a network engineer, you can study them in detail and you can make sure you follow these standards and enforce it in your organization. Now, the 802 LAN or MAN standards includes the Ethernet. Okay, Ethernet is a special kind of local area network. Now, again, we study it has got two sublayers. One is LLC, logical link control, and the other one is MAC, okay, media access control. So as we studied in our lecture, LLC places information in the frame to identify which network layer protocol is used. And MAC, responsible for data encapsulation and media access control, and provides addressing. What kind of addressing? Hardware addressing. Okay, we are talking about hardwired addressing. We are talking about base 16 hexadecimal addressing. So let's look at our media access control. This sublayer is responsible for data encapsulation and accessing the media. This standard is given in IEEE 802.3. It encapsulates, okay, by looking at three main things. Okay, so data encapsulation includes the following. Number one, Ethernet frame. Okay, this is the internal structure of the Ethernet frame. Number two, Ethernet addressing. Okay, when I say addressing, it includes both the destination address and the source address. Which address are we talking about? We are talking about layer 2, data link layer address, which is your MAC address. The layer 3 network layer address is your IP logical address. Layer 2 data link layer address is your MAC physical address. Okay. It also has error detection. So much error detection algorithms and protocols we studied in our lecture yesterday. So Ethernet layer error detection. The Ethernet frame includes a frame check sequence, FCS trailer. That FCS will make sure that there is no error in the frame that is sent. The IEEE 802.3 MAC sub-layer includes specifications for different Ethernet communications. Okay. Now, as we studied earlier, if you're using legacy Ethernet like bus topology or a special topology which uses old hubs, then you use a half duplex medium. In half duplex medium, you have to wait until you can send your data. Just now we studied the CSMA-CD and CSMA-CA. Okay. Of course, CSMA-CD and CSMA-CA. CD, collision detection, CA, collision avoidance. Okay. Now they follow our half duplex medium. But if you're using your switches we studied earlier, it is on full duplex mode. Okay. You can send and receive at the same time. Ethernet LANs of today use switches that operate in full duplex mode. Okay. So let's look at your minimum Ethernet frame. Look at your minimum, look at your Ethernet frame. The minimum size for an Ethernet frame is 64 bytes. Okay. Now the data that you transfer can range from 45 bytes to 1,500 bytes. Okay. They say over here, if the size that you are transferring is beyond certain size, then we call it jumbo frame. Okay. Now, in the beginning, you have got preamble and SFT. Okay. The preamble and SFT will be 8 bytes. Then you have got your MAC address, which is the destination MAC address, 6 bytes, where it has to go. The source MAC address, another 6 bytes. Okay. What type of data? 2 bytes. The actual payload can range from 45 to 1,500, but its minimum size should be 64. And your error check, remember FCS, frame check sequence, which makes sure that the data is okay, is 4 bytes. Any frame less than 64 bytes in length, okay, is considered a collision fragment or run frame and is discarded. Okay. Frames with more than 1,500 bytes of data, we call it jumbo or baby giant frames. Okay. So these kind of frames, jumbo or baby size frames, they are considered invalid. Jumbo frames are usually supported by fast Ethernet or gigabit Ethernet switches and NICs. Okay. Now let's look at Ethernet MAC address. An Ethernet MAC address consists of a 48-bit binary value. Okay. When you say 48-bit binary value, 8 bits will make 1 byte. Okay. So if you divide 48 by 8, that will make it how many bytes, my dear students? Anyone? How many bytes is a MAC address? Anyone? 48 bits. 48 divided by 8 is, yes, 6 bytes. Okay. So it is expressed, your MAC address is expressed in base 16 hexadecimal address. Okay. So remember that. When using hexadecimal, leading zeros are always displayed to complete the 8-bit representation. For example, the binary value 00001010 is represented in hexadecimal as 0A. And we did the lesson where we do the conversion. This is converted into 0, and this is converted into A. Okay. Hexadecimal numbers are often represented by the value preceded by 0x. So the moment you see this, you know, hey, this is a hexadecimal address. And hexadecimal means it is a MAC address. Okay. So let's look at a little bit more detail. In an Ethernet LAN, every network device has got a MAC address. Okay. So Ethernet MAC address is 48-bit and it is using 12 hexadecimal digits. Okay. So that would be 12 hexadecimal digits. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 6 plus 6. 6 plus 6 is 12. Now, all MAC addresses must be unique to the Ethernet device or Ethernet interface. That means every MAC address in this world should be unique. There should not be a duplicate MAC address. My Samsung phone and my Vivo phone should not have the same MAC address. Okay? There should be no conflict. Now the question is, how is this achieved? Very simple. You go to IEEE and you ask IEEE, please give me a OUI, that is Organizationally Unique Identifier. Now IEEE will say, hey, Samsung, this is your OUI. Okay? Now Huawei, this is your OUI. Okay? My OUI will be a 3-byte consisting of 6 digits. See, 1, 2, 3, 4, 5, 6. Hexadecimal value given to me by IEEE. Now, I go back to my factory and I add another 3 bytes, another 6 hexadecimal values inside it. This will be render assigned OUI. Now, this will make sure that every MAC device, every device with a MAC is unique in this world. There is no MAC which is repeated. If at all it is repeated, that means the vendor has done some mistake, okay? And has to close factory, has to close shop, okay? Because IEEE doesn't make the mistake, okay? So this situation makes sure that every MAC in the world we have is unique and is not repeated, okay? So an Ethernet MAC address consists of a 6 hexadecimal vendor OUI code followed by a 6 hexadecimal vendor assigned value. So this one, the vendor takes care of it. This one is given by IEEE. So when a device is forwarding a message to an Ethernet network, the Ethernet header includes a source MAC address and a destination MAC address. Okay? So based on that, when it goes to the switch will check. Okay? For example, over here, if your NIC receives a message from the switch, it examines the destination MAC address. For example, this one is sending to see if it matches the physical MAC address that is stored in the RAM. If there is no match, the device discards the frame. If there is a match, it passes the frame up the OSI layer. Long story short, all these devices are connected to the switch, and the switch has got a table. And in that table, it has stored all the MAC addresses. And once it receives a MAC from the source, it knows which destination to send to. Okay? And remember, a switch is a full duplex device. That means it can send and receive at the same time. So there is no collision domain. A hub, unfortunately, is a collision domain. But switch, it will send your address to the destination. Okay? So any device that is the source or destination of an Ethernet frame will have an Ethernet NIC and therefore a MAC address. So any device on the network, okay, even IoT devices, all of them should have a MAC address. Now, in Ethernet, different MAC addresses are used for layer 2, unicast, broadcast, and multicast communications. Okay, so a unicast MAC address is the unique address that is used when a frame is sent from one device directly to another device. Okay, so from this MAC address to the destination MAC address, as long as you have the as long as you have the table inside the switch, you can find it very easily. Okay, so the destination MAC and the source MAC will be part of the frame, okay, and it will be sent. The process that the source host uses to determine the destination MAC address is associated with a IP version 4 address. So how does it associate it with the IP version 4 address? The process is known as ARP, also known as Address Resolution Protocol. The process that the source host uses to determine the destination MAC address in case of IP version 6 is known as ND. ND stands for Neighbor Discovery. Okay, so if you want to convert, okay, from MAC to IP version 4, use ARP. From MAC to IP version 6, use ND. Remember, your source address should always be a unicast address. Okay. In case of multicast, or for that matter, let's go to first broadcast first. A broadcast address has got a specific MAC address. So what is the MAC address, broadcast address? It is FFFFFFFFFFF. See, 12 Fs. This one means it is a broadcast address. This one means every device on the network will receive this, this message, this data that comes with this. Okay, the user data will be received by every device on the network. And not only MAC broadcast address, we also have IP broadcast address. For example, remember, look at this. If the subnet mask is 255.255.255.0, you know that the host portion is 8 bits. Okay, so the moment you see 255, you know that this is the broadcast address. How? Because the host portion can only have address starting from 1 until 254. Why not 255? Because 255 has been reserved as a broadcast address. You cannot give an IP address as 255. 255 is the IP version 4 reserved for broadcast address. Okay. So over here, 255, if you convert it into binary form, that means all will have ones. That means it will be 1111 1111. Translate into decimal, 255. Translate into binary, it will be 8 ones. Okay, so this address is reserved. Okay, this is reserved for broadcast. In MAC, when you have got 12 apps, that means it is a broadcast address. When you send to a multicast, then that means you're sending to a series of devices. Okay, so for example, this may be a series of multicast address. So you will have a multicast address, for example, 0100FE will be your multicast address. Okay. So there is a destination MAC address of 0100FE when the encapsulated data is an IP version 4 multicast packet. Okay. And the destination MAC address of 3333 when the encapsulated data is an IP version 6 multicast packet. So when you have something like this, we know that it's IP version 4, and this one is IP version 6. Okay. So when you send an IP multicast frame, you know that only certain computers who are in that list will get that address. Okay. Now let's look at more at the MAC address table. Today's lab will be mostly dealing with looking at the switch's MAC address and your computer's MAC address. So the data link layer Ethernet switch uses layer 2 MAC address to make the forwarding decisions. Okay. It is completely unaware of the data protocol that is being carried in the data portion of the frame. It doesn't know IP version 4 messages or ARP messages or IP version 6 ND packet. It doesn't know anything. It only knows MAC address. It has got a table with a list of all the MAC address. Okay, that is why data link layer is very important. It has to take the IP address in the network layer and convert it into MAC address. Okay. So when you switch on your switch for the first time, its MAC address table is empty. That is why usually when you're having an enterprise and organization, you don't switch off your switch. It has to remain on. Why? Because its MAC table needs to be always in the memory. If you switch it off, it goes away. Okay. That is why the MAC address table is sometimes referred to as content addressable memory. And every time you connect a device to the network, that table, the MAC table, will be updated. Usually it is updated every 5 minutes. Okay, there. So a switch's MAC address table is always learning. Okay, actually, by default, most Ethernet switch keep an entry in the table for 5 minutes. After 5 minutes, it again checks the network. Are there any new devices in the network? Are there any new devices in the network? Are there any new devices in the network? The moment you add a device to the switch, so that table will be updated. Okay, and this is, remember, switch connects nodes within the same network, within the same IP address. When I say same IP address, I mean same network address. Okay, the host may be different, but network address should be the same. Okay, so it keeps checking the nodes. So it will be in the learning phase to make sure that what new devices you are adding. Okay. So looking at that table, if the destination MAC address is a unicast address, the switch will look for a match between the destination MAC address of the frame and the entry in its MAC address table. If the destination address is in the table, it will forward it immediately to the destination MAC address. If it is not in the table, the switch will forward the frame to all ports except the incoming port. Okay, so it will forward it until it has found it. If it is a frame that is not within the network, then it will forward it to the router. Okay, except it will forward to all ports except the incoming port, so that there is no collision. Okay. So as a switch receives frames from different devices, it is able to update its MAC address. You see, every time you connect to a port on the switch, you are updating the table inside the switch, which has a list of all the MAC addresses. Okay. When the MAC address table of a switch contains the destination MAC address, it is able to filter the frame and forward out a single port. Okay. That is why when you create a VLAN in your switch, that VLAN can be also regarded as a single MAC address. Okay. Now let's look at switch speeds and forwarding methods. So the switch uses one of the following forwarding methods. It can be store and forward switching. It can be cut-through switching. In store and forward switching, the frame forwarding method receives the entire frame and computes the CRC. Remember we studied CRC in yesterday's lecture, the cyclic redundancy code. If the CRC is valid, the switch will look for the destination address, okay? And then it will forward it. One of the advantages of store and forward switching is it determines if a frame has errors, okay? So that will usually ensure that there is a good quality of service, okay? Especially in converged networks, when you are sending data, voice, and video through the same medium. What about the second one, cut-through switching? In that, the switch acts upon the data as soon as it is received, even if the transmission is not complete, okay? It uses buffers to read out the destination MAC address so that it can determine to which port it should forward out the data, okay? So we have got two kinds of cut-through switching, fast-forward switching and fragment-free switching. So without going into the details, an Ethernet switch may use a buffering technique to store frames before forwarding them or when the destination port is busy. So this can be based on the congestion of the network. It can be a method which they use is port-based memory or shared memory, okay? We won't go into the details of that. You can study it later. Now, two of the most basic settings on a switch are the speed of the switch. It can be the duplex settings, okay? Is it full duplex or half duplex? Usually, most of our switches we use these days are full duplex. Half duplex are in the olden days, okay? If you're using a gigabit Ethernet, you can only use full duplex. Most of the Ethernet we use, local area connection Ethernet we use is our gigabit Ethernet, which is using full duplex. Half duplex was something that we used to use in the olden days, okay? If you're connecting a full duplex with a half duplex, you are slowing down your network, okay? So because in a full duplex, you can send whatever you want. Half duplex, you have to wait to make sure that there is no collisions, okay? That is why we don't use hubs in our networks anymore. All the switches are full duplex, okay? Another aspect of our fast networking devices that we use today are devices which are having AutoMdix. What does that mean? That means it doesn't matter if you use a straight through cable or you use crossover cable. Your device will automatically negotiate, okay, what kind of connection you have. I mean, what kind of wire you have. Usually, let's go through this. Connections between devices once require the use of either a crossover or straight through cable, okay? For example, the type of cable required depended on the type of interconnecting devices. A direct connection between a router and a host requires a crossed over connection. Okay, so let's just go to packet tracer. Okay, if I have a switch, sorry, over here, the cable required, okay, a direct connection between a router and a host requires a crossover connection. So if I have a router here, let's say router 6, and a computer, which is my host, a device, a generic computer. So in order to connect them together, by law, it's supposed to use, you see over here, it says crossover connection. You're supposed to use a crossover, fast Ethernet 0 to gigabit Ethernet 0. Okay. We are supposed to use a crossover connection. Okay. Now, if I give an IP address to the 0, let's say I give an IP address to the PC, let's go here, give an IP address, let's say 192.168.10.10. Okay, there. This is my subnet mask. Okay, and here, let's open it, go to the command line interface, enable conf T interface G0/0. Okay, IP address 192.168.1 sorry, not 1.10.1. Okay, subnet mask 255.255.255.0. No shut. Exit, exit. Okay, there you see there is a network connection. Okay, now theoretically it tells me, hey, you cannot do this without the crossover cable. Now let's try another connection, another generic computer, but this time what I do is I connect to the other side, okay, to the port gigabit Ethernet 01. But this time I use a straight through cable. I don't follow the rule. Okay, I follow my own rule and connect to gigabit Ethernet 1. So convention and wisdom says that this is not possible. You're not supposed to do that. So let's see. Let's say here. Remember, this should be a different network. It cannot be the same network. So I say 192.168.1.1.10. Okay, the previous one was 10. So here I make it 1. Okay. Now here I go in the router. Conf T interface gigabit 0, 1. Okay. Now I say IP address 192.168.1.1. That would be my first address, 255.255.255.0. No shut. So the state is up, exit. So let's see. There. Now the question is, how is it possible? It says over here, a direct connection between a router and a host requires a crossover connection. I just broke that rule. Can you see that? How is it possible? I'll tell you how is it possible. Because my router has got AutoMdix. Okay? So what is AutoMdix? Most switches and routers now support automatic medium dependent interface crossover, AutoMdix feature. What does it do? The switch automatically detects the type of cable attached to the port and configures the interface accordingly. Okay? So even the router, it doesn't care what can, if you are using a straight through, it will detect and it will adjust its algorithm so that the data can still pass. Okay, so this is something new that we have. Okay, so we don't have to memorize. In early days when I was networking, I could not do this, my dear students, because the router I used to use was old. I had to only do this. But now we don't have that issue. Okay? Even for switches. Okay? But you know what? You can disable that feature if you want to be, if you want to be cruel to your students. You disable the MDIX feature and then give the router and the switch to the students and then tell them to do their exam. And then you just sit back and enjoy the show. I'm kidding. I won't do that, my dear students. Okay, relax. But you can disable the AutoMdix feature. Okay, but why would you want to do that? Okay, it's better to just use that feature so that your router and your switch are cable independent. Okay. But remember, your PC to PC, you still have to use a crossover. It doesn't have an AutoMdix feature, but perhaps in future we may have it. Okay. So that brings us to the end of this session. Anyone has any questions related to today's presentation first?